Assalamualaikum and hello everyone. So in this video, we are presenting to you Kirchhoff's Voltage Law. We hope that everybody understand everything throughout this video. Have a good day and enjoy.
A German physicist, Gustav Robert Kirchhoff, made his first outstanding research contribution which related to electric current. Kirchhoff's law, which he announced in 1845, allowed calculation of currents, voltage and resistance in electrical circuits with multiple loops, extending the words of ohms. Kirchhoff's first law states that the sum of current into a given node equal to the sum of the current out of the node. Kirchhoff's first law is also known as Kirchhoff's current law. The definition of Kirchhoff's voltage law states that the algebraic sum of all voltage around a closed path or loop is zero. Kirchhoff's voltage law is also be called as loop rule. For conceptual understanding, the loop rule is equivalent to the principle of conservation of energy. Any charge that moves around any closed loop in a circuit, starting and ending at the point, must gain as much energy as it lost. In simple, we can say that the sum of voltage drops is equal to the sum of voltage rise. The first one, it is important that we need to pay special attention to algebraic sign, plus and minus, of the voltage drop across elements and the EMF of sources. Otherwise, our calculation may be wrong.
Please be reminded, because this is so important. We need to pay special attention to the algebraic signs, which is either positive or negative, of the voltage drops across elements and the EMF of sources. Otherwise, our calculations may be wrong.
For this simple example, we will assume the current I is in the same direction as the flow of positive charge, that conventional current flow. Here, the flow of current through the resistor is from point A to point B, that is from positive terminal to a negative terminal. Thus, as we are traveling in the same direction as current flow, there will be a fall in potential across the resistive element, giving rise to the negative IR voltage drop across it. If the flow of current was in the opposite direction from point B to point A, then there would be a rise in potential across the resistive element as we are moving from A negative potential to A positive potential, giving us a positive IR voltage drop. Thus, to apply Kirchhoff's voltage law correctly to a circuit, we must first understand the direction of the polarity. As we can see, the sign of voltage drop across the resistive element will depend on the direction of the current flowing through it. As a general rule, we will lose potential in the same direction of current across an element, and we will gain potential as you move in the direction of an EMF source. The direction of current flow around a closed loop can be assumed to be either clockwise or anticlockwise, and either one can be chosen. If the direction chosen is different from the actual direction of current flow, the result will still be correct and valid, but will result in algebraic answer having a minus sign. Since here we have two resistors, R1 and R2 are wired together in series connection, they are both part of the same loop, so the same current must flow through each resistor. We can see that by applying Kirchhoff's voltage law to this single closed loop, we'll produce the formula for the equivalence or total resistance in the series circuits, and we can expand on this to find the values of the voltage drop around the loop. Thus, we can get the voltage drop across resistor R1 is equal to I times R1, and the voltage drop across resistor R2 is equal to I times R2.
Moving on to Kirchhoff's voltage law example number 1. Three resistors of values 10 ohms, 20 ohms, and 30 ohms respectively are connected in series across a 12 volts battery supply. Thus, there are 5 questions for us to answer each. And as you can see on the right side of the video, there is a figure that will help us to answer this question. Question A. Find the total resistance, which we can also write it as RT, which means total resistance. So RT is equal to R1 plus R2 plus R3 because in series, we know that the total resistance is actually the summation of all resistors. Therefore, we get the answer as 60 ohms. Question B. Find the circuit current. As we all know, V is equals to IR according to Ohm's law. Therefore, I is equal to Vs over RT. Vs here means voltage source and RT means total resistance, which we will calculate it as 12 volts over 60 ohms equals to 0.2 ampere.
Question C. Calculate the current through each resistor. As we know, the resistors are wired together in series. They are all part of the same loop. Therefore, each of them experiences the same amount of current. Thus, current in R1 equal to current in R2 equal to current in R3 equal to current in series. Therefore, current is equal to 0.2 amperes. Question D. Calculate the voltage drop across each resistor. Here, we already know that the current for each resistor is 0.2 amperes, right? So, we can use formula V equal to IR to find each voltage drop. Therefore, voltage for R1 is 0.2 times 10 equal to 2 volts. Voltage for R2 is 0.2 times 20 equal to 4 volts. And voltage for R3 is 0.2 times 30 equal to 6 volts. And the last question, E. Verify Kirchhoff's voltage law. Kirchhoff's voltage law tells us that the sum of the voltage difference around any closed loop in a circuit must be equal to 0. Therefore, Vs plus negative IR1 plus negative IR2 plus negative IR3 must be equal to 0. Then we must substitute the values for Vs, current and resistor. And lastly, we will get 0 for the last answer.
As you can see in a given circuit that the single voltage source is linked with the passive element, the electric element which does not produce power like a resistor, which have B, C, D, E, F voltage about them. As all these elements are connected in series, so the voltage value will be added. If we apply KVL, we say voltage around the electric element which does not produce power like a resistor, element in circuit always equivalence and reverse to source voltage. Therefore, the summation of the voltage change across all the elements in circuit is always equal to 0. In this slide, we have mesh analysis. It is the method to help us to find the current and voltage in any closed loop working with the KVL. By this analysis, we can find values of current and voltage across any component of the loop on the circuit. There are 3 steps to apply this mesh analysis. Firstly, allocate discrete current values to every enclosed circle of the network. After that, apply Kirchhoff's voltage law about every enclosed circle of the system. Lastly, resolve the resultant concurrent linear equation to find the value of current in the ring. This is the example of KVL. In the given diagram, a circuit is drawn at which we have to apply KVL. In this circuit, there are 3 loops which are labeled in the circuit by number 1, number 2, and number 3. We will apply KVL on these 3 loops one by one and we will get corresponding equation. When we apply KVL to the first loop, we will get this equation. V1 equal to I1 times R1 plus R3 times I1 plus I2. 10 equal to I1 times 10 plus 40 times I1 plus I2. We will get 10 equal to 50 I1 plus 40 I2. After applying KVL on the first loop, we will now apply it on the second loop. Then we will get the equation for this loop. After finding the equation for loop first and second, now we will find the equation for third loop. V1 minus V2 equal to I1 times R1 minus I2 times R2. 10 minus 20 equal to 10 I1 minus 20 I2. By solving equation of loop 1 and second, we will get the value of I1 and I2, which are mentioned below. I1 equal to negative 0.143 ampere and I2 equal to positive 0.429 ampere. By using the value of I1 and I2, now we can find the value of I3. I3 equal to I1 plus I2. By putting the value of I1 and I2, we can get the current at resistance R3. I3 equal to negative 0.143 plus 0.429, and we will get 0.286 ampere for I3. I3 is the current which is passing through the resistance R3. We can also find the value of voltage across this resistance by using I3. V3 equal to 0.286 times 40, and we will get 11.44 volt. This slide is about application of KVL law. These are some important applications of KVL law. Kirchhoff's law are used to measure the unknown standards such as current, voltage, and also the direction of current moving in the circuit. This rule is applicable to every circuit, but is very fruitful to solve complicated circuitries. This law also helps us to observe the transfer of power in the circuit.
Thank you for watching.